Unveiling the power of data mining. Transforming raw information into actionable insights. Data mining has emerged as a pivotal field, evolving from basic statistical analysis and database management systems. Its roots can be traced back to the mid-20th century when early statistical methods were used to analyze data. As databases grew in complexity, the need to extract meaningful patterns increased, leading to the development of knowledge discovery techniques. The 1980s witnessed the rise of expert systems and machine learning, which contributed to the automation of data analysis. The term, data mining, gained popularity in the 1990s with the increasing availability of large datasets and affordable computing power. This era saw the development of core data mining algorithms and techniques that are still in use. Today, data mining has transformed, integrating with big data technologies and artificial intelligence to address complex challenges and unlock insights from massive, diverse datasets. This evolution reflects a continuous drive to derive value from data across various domains. Importance in the digital age. The digital age is characterized by an unprecedented volume of data generated from diverse sources, rendering data mining increasingly vital. Organizations across industries recognize the strategic advantage of extracting knowledge from this data deluge. Data mining enables businesses to understand customer behavior, optimize operations, and personalize services. It supports scientific discovery by identifying patterns in complex datasets, accelerating research in fields like genomics and astronomy. In healthcare, data mining improves diagnostics, predicts disease outbreaks, and personalizes treatment plans. Governments utilize data mining for fraud detection, security enhancement, and policymaking. The capability to transform raw data into actionable intelligence is a defining characteristic of data-driven decision-making, making data mining an indispensable tool for organizations seeking to thrive in the modern landscape. The rise in digital data has also created opportunities for reinforcement learning to analyze big data, although challenges related to data privacy remain. The scope includes defining core concepts, exploring various data mining algorithms, and examining real-world applications across diverse industries. This exploration will address the challenges and limitations of data mining, particularly in the context of big data. Finally, it discusses emerging trends such as integration with artificial intelligence, real-time data mining, and edge computing applications. The primary goal is to provide a thorough understanding of data mining's capabilities and its transformative impact on decision-making processes across different sectors. Data mining is the process of discovering patterns, correlations, and other useful information from large datasets. It involves using techniques from statistics, machine learning, and database management to extract knowledge that can be used to support decision-making. Core concepts include data preprocessing, which involves cleaning and transforming raw data into a suitable format for analysis. Pattern discovery is the process of identifying interesting and non-trivial patterns within the data. Data mining aims to uncover previously unknown and potentially valuable insights, turning raw data into strategic assets. It is an interdisciplinary field, drawing upon expertise from computer science, statistics, and domain-specific knowledge to achieve its objectives. Types of data mining techniques. Various data mining techniques exist, each suited for specific tasks and data types. Classification is used to assign data instances to predefined categories based on their attributes. Regression analysis predicts a continuous value based on input variables. Clustering groups similar data instances together based on their inherent characteristics. Association rule mining identifies relationships between items in a dataset, such as products frequently purchased together. Anomaly detection identifies unusual data points that deviate significantly from the norm. Each technique offers a unique approach to extracting knowledge from data, and the selection of an appropriate technique depends on the specific problem and the nature of the data being analyzed. Text mining is another technique that helps in harnessing the power of unstructured textual data by analyzing it to extract new knowledge and to identify significant patterns and correlations hidden in the data. The data mining process typically involves several key stages, forming a structured approach to knowledge discovery. These stages ensure that data mining projects are well-defined, efficient, and produce meaningful results. Data collection and preparation. The initial stage involves collecting data from relevant sources and preparing it for analysis. Data collection can involve gathering information from databases, data warehouses, web sources, and other repositories. Data preparation includes cleaning the data to handle missing values, noise, and inconsistencies. Data transformation involves converting the data into a suitable format for data mining algorithms, such as normalization or discretization. Feature selection is used to identify the most relevant attributes for analysis, reducing dimensionality and improving model performance. This stage is critical as the quality of the data directly impacts the accuracy and reliability of the discovered knowledge. Preprocessing methods, such as replacing missing values, standardization, and outlier removal, may be necessary for social insurance data. The data must also be handled with care regarding interpretability and relevance in relation to both institutional and personal processes. Pattern discovery. This stage involves applying data mining algorithms to identify patterns and relationships in the prepared data. The choice of algorithm depends on the specific data mining task, such as classification, clustering, or association rule mining. Algorithms are applied to the data to uncover hidden patterns, correlations, and anomalies. Evaluation metrics are used to assess the quality and significance of the discovered patterns. This stage requires careful selection of algorithms and parameter tuning to achieve optimal results. Several machine learning algorithms exist, and the selection of the appropriate algorithm depends on the dataset, feature selection method, and model development technique. Knowledge interpretation. The final stage involves interpreting the discovered patterns and presenting them in a meaningful way. This includes visualizing the results using charts, graphs, and other visual aids. The discovered knowledge is evaluated for its usefulness and relevance to the problem domain. Actionable insights are derived from the patterns, which can be used to support decision-making. The knowledge is documented and disseminated to stakeholders. This stage ensures that the discovered knowledge is effectively translated into practical applications and business strategies. Data mining algorithms and techniques. Classification algorithms. Classification algorithms are a fundamental set of techniques used to assign data instances to predefined categories based on their attributes. These algorithms learn from a training dataset, where the correct classifications are known, and then apply this knowledge to classify new, unseen data. Common classification algorithms include decision trees, support vector machines, SVMs, and naive Bayes classifiers. Decision trees create a tree-like structure to classify data based on a series of decisions made at each node. SVMs find the optimal hyperplane that separates data points into different classes with the maximum margin. Naive Bayes classifiers use Bayes' theorem to calculate the probability of a data instance belonging to a particular class, assuming independence between the attributes. These algorithms are widely used in applications such as spam detection, image recognition, and medical diagnosis, where the goal is to predict the category or class of a new instance. Supervised learning algorithms, such as naive Bayes, decision tree algorithm, and CN2 rule induction, can be used to classify individuals based on preprocessed data. In the context of lung cancer diagnosis, machine learning classification algorithms like naive Bayes, support vector machine, artificial neural network, and logistic regression are used. Clustering techniques. Clustering techniques group similar data instances together based on their inherent characteristics without prior knowledge of the categories. These techniques are used to discover underlying structures and patterns in data, making them valuable for exploratory data analysis. Common clustering algorithms include K-means, hierarchical clustering, and DBSCAN. K-means partitions data into K-clusters, where each data point belongs to the cluster with the nearest mean. Hierarchical clustering builds a hierarchy of clusters, starting with each data point as a separate cluster and iteratively merging the closest clusters until a single cluster is formed. Clustering is used in various applications, such as customer segmentation, anomaly detection, and image analysis, where the goal is to identify groups of similar data instances. Association rule mining. Association rule mining is a technique used to discover relationships between items in a dataset, often applied to transaction data to identify items that are frequently purchased together. The goal is to identify strong association rules that indicate the likelihood of certain items occurring together in a transaction. The a priori algorithm is a widely used association rule mining algorithm that iteratively identifies frequent item sets and generates association rules based on these item sets. Association rule mining is used in retail, e-commerce, and other industries to improve product placement, recommend products to customers, and optimize marketing campaigns. A neutropsophic association rule algorithm can be used to generate association rules by dealing with membership, indeterminacy, and non-membership functions of items. Regression analysis. Regression analysis is a statistical technique used to model the relationship between a dependent variable and one or more independent variables. The goal is to predict the value of the dependent variable based on the values of the independent variables. Linear regression is a simple form of regression that assumes a linear relationship between the variables. Multiple regression extends linear regression to include multiple independent variables. Nonlinear regression models more complex relationships using nonlinear functions. Regression analysis is used in various applications, such as forecasting sales, predicting stock prices, and modeling scientific phenomena, where the goal is to estimate the value of a continuous variable based on other variables. Support vector machine, SVM, and linear regression can be used to forecast PV output based on data collected from sensors. Neural networks and deep learning in data mining. Neural networks are a powerful class of machine learning models inspired by the structure and function of the human brain. They consist of interconnected nodes, neurons, organized in layers, which process information through weighted connections. Deep learning is a subset of neural networks that uses multiple layers, deep neural networks, to learn complex patterns from data. Deep learning models have achieved remarkable success in various tasks, such as image recognition, natural language processing, and speech recognition. In data mining, neural networks and deep learning are used for classification, regression, clustering, and other tasks, particularly when dealing with complex and high-dimensional data. Deep learning's ability to automatically learn features from raw data makes it valuable for uncovering hidden patterns and relationships. Deep learning is integrated with Bayesian optimization to enhance the implementation of iterative algorithms in software and to help the automatic initialization and optimization of hyperparameters. Google's DeepMind has used deep learning technology to develop their AlphaFold tool to make predictions for protein folding. Applications of data mining. Data mining plays a vital role in business intelligence and market analysis, enabling organizations to gain insights into customer behavior, market trends, and competitive landscapes. By analyzing transaction data, customer demographics, and online activity, businesses can identify customer segments, predict purchasing patterns, and personalize marketing campaigns. Data mining helps businesses optimize pricing strategies, improve supply chain management, and detect fraudulent transactions. Market analysis uses data mining to identify market opportunities, assess competitive threats, and track brand performance. Ultimately, data mining empowers businesses to make data-driven decisions, improve operational efficiency, and enhance customer satisfaction, providing a competitive edge in the marketplace. Healthcare and medical diagnosis. In healthcare, data mining improves medical diagnosis, treatment planning, and healthcare management. By analyzing patient records, medical images, and genomic data, data mining identifies disease patterns, predicts patient outcomes, and personalizes treatment plans. It helps detect outbreaks of infectious diseases, optimize hospital resource allocation, and reduce healthcare costs. Machine learning algorithms are used to analyze medical images for early detection of diseases like cancer and to predict the risk of chronic conditions like diabetes and heart disease. The integration of big data and machine learning has created differences in data science and a big influence on applications in the medical field, especially in response to COVID-19. Analyzing social insurance data can also help to identify the insured and uninsured. Financial services and fraud detection. Data mining is used extensively in financial services for risk management, fraud detection, and customer relationship management. By analyzing transaction data, credit scores, and customer demographics, financial institutions can identify high-risk customers, detect fraudulent transactions, and prevent money laundering. Data mining helps banks and insurance companies assess credit risk, predict loan defaults, and optimize pricing strategies. It also improves customer service by personalizing financial products and services based on individual customer needs. Effective use of machine learning algorithms can anticipate accurate outcomes in the world of nursing. E-commerce companies utilize data mining to enhance customer experience, personalize product recommendations, and optimize marketing campaigns. Data mining helps optimize website design, personalize email marketing, and target advertising campaigns. Recommendation systems use data mining algorithms to predict customer preferences and provide personalized recommendations, increasing sales and customer loyalty. High-throughput screening, HTS, improves decision-making in drug discovery. Scientific research and discovery. Data mining accelerates scientific research and discovery across various disciplines. By analyzing large datasets generated from experiments, simulations, and observations, scientists can identify patterns, test hypotheses, and develop new theories. Data mining is used in genomics to identify gene-disease associations, in astronomy to discover new celestial objects, and in environmental science to model climate change. It helps researchers uncover hidden relationships, validate models, and make predictions, leading to new scientific breakthroughs. In animal sciences, machine learning and data mining are expected to be instrumental in helping meet the challenges facing global agriculture. Machine learning algorithms can be used to analyze DNA sequence data for sequence alignment, classification, clustering, and pattern mining. Integrative analyses across distributed data resources are essential for untangling the biological complexity of mental illnesses. Big data and data mining. Challenges of mining big data. Mining big data presents unique challenges due to its volume, velocity, variety, and veracity. The sheer volume of data requires scalable algorithms and high-performance computing infrastructure. The velocity of data streams necessitates real-time processing and analysis. The variety of data types, including structured, semi-structured, and unstructured data, requires flexible and adaptable data mining techniques. The veracity of data, including noise, inconsistencies, and biases, requires robust data cleaning and validation methods. Addressing these challenges requires specialized tools, techniques, and expertise to extract meaningful insights from massive and complex datasets. Traditional data mining tools may not be able to handle big data effectively. Distributed and parallel data mining. Distributed and parallel data mining techniques are essential for processing large datasets that cannot be handled by a single machine. Distributed data mining involves partitioning the data across multiple machines and performing data mining tasks in parallel. Parallel data mining uses parallel processing techniques to speed up the execution of data mining algorithms on a single machine or a cluster of machines. Common distributed and parallel data mining frameworks include Hadoop and Spark, which provide scalable and fault-tolerant platforms for processing big data. These techniques enable organizations to analyze massive datasets efficiently and effectively. Cloud-based data mining solutions offer scalable, cost-effective, and accessible platforms for data analysis. Cloud providers offer a range of data mining services, including data storage, data processing, and machine learning tools. These services enable organizations to leverage the power of the cloud to analyze large datasets without investing in expensive hardware and software infrastructure. Cloud-based data mining solutions provide flexibility, scalability, and ease of use, making them attractive for organizations of all sizes. The new development, especially in cloud computing and data transaction speed, offers significant advantages to the practical use of AI applications. Data mining tools and software. Open source data mining tools provide free and flexible platforms for data analysis, offering a wide range of algorithms and techniques. Popular open source tools include Weka, R, and Python. R is a programming language and environment for statistical computing and graphics, widely used for data analysis and visualization. Python, with libraries like scikit-learn, pandas, and TensorFlow, provides a versatile platform for data mining and machine learning. Open source tools offer transparency, customization, and community support, making them attractive for researchers and practitioners. These tools can handle large volumes of data as well as evolving data streams. Commercial data mining platforms offer comprehensive solutions for data analysis, providing advanced features, scalability, and enterprise-level support. These platforms offer a range of data mining algorithms, data integration tools, and visualization capabilities. They provide user-friendly interfaces and automation features, simplifying the data mining process for business users. Commercial platforms offer robust security, compliance, and governance features, making them suitable for organizations with strict data management requirements. Different data mining software tools offer varying strengths and weaknesses, depending on the specific needs and requirements of the user. Open source tools like Weka, R, and Python provide flexibility and customization but may require more technical expertise. Commercial platforms like IBM SPSS Modeler, SAS Enterprise Miner, and Rapid Miner offer advanced features and enterprise-level support but come at a higher cost. The choice of software depends on factors such as data volume, complexity, analytical requirements, budget constraints, and user skills. Evaluating the features, performance, and cost of different tools is essential for selecting the most appropriate software for a given data mining project. A numerical example for explorative analysis of data can be applied using Orange. An R package called Big Lasso extends the lasso model fitting to big data in R. Integration of Hadoop and R is the best combination in the field of distributed computing and analytics. Ethical considerations in data mining. Privacy concerns and data protection. Data mining raises significant privacy concerns as it involves collecting, analyzing, and using personal data. The potential for misuse of data, such as discrimination, profiling, and surveillance, requires careful consideration of ethical and legal implications. Data protection regulations, such as the General Data Protection Regulation, GDPR, impose strict requirements on data collection, processing, and storage to protect individuals' privacy rights. Organizations must implement privacy-enhancing technologies, such as anonymization and pseudonymization, to minimize the risk of data breaches and unauthorized access. Data privacy is one of the most important challenges facing data analysis. Bias and fairness in data mining algorithms. Data mining algorithms can perpetuate and amplify biases present in the data, leading to unfair or discriminatory outcomes. Biased data can result from historical prejudices, sampling errors, or incomplete information. Algorithmic bias can affect decisions in areas such as hiring, lending, and criminal justice, with significant consequences for individuals and groups. Organizations must carefully evaluate their data and algorithms for bias and implement fairness-aware techniques to mitigate these biases. This includes using diverse and representative datasets, auditing algorithms for bias, and implementing fairness metrics to evaluate model performance. Explainable AI (XAI) techniques can help understand how algorithms make decisions and identify potential sources of bias. Regulatory frameworks and compliance. Various regulatory frameworks and compliance standards govern data mining activities, aiming to protect privacy, ensure fairness, and prevent misuse of data. The GDPR sets strict rules for data processing and requires organizations to implement data protection measures. Industry-specific regulations, such as the Health Insurance Portability and Accountability Act, HIPAA, in healthcare and the Fair Credit Reporting Act, FCRA, in finance, impose additional requirements on data handling. Organizations must comply with these regulations and standards to avoid legal penalties, reputational damage, and loss of customer trust. Compliance requires establishing data governance policies, implementing data security measures, and conducting regular audits to ensure adherence to regulatory requirements. Future trends in data mining: integration with artificial intelligence. Integration of data mining with artificial intelligence, AI, is a significant trend, enabling more sophisticated and automated data analysis. AI techniques, such as machine learning and deep learning, enhance data mining capabilities by automatically learning patterns and making predictions. Data mining provides AI with the data needed to train and improve models. This synergy between data mining and AI drives advancements in areas such as natural language processing, computer vision, and robotics. The progression of big data analytics framework must be clearly understood so that novel approaches can be developed to advance this state-of-the-art discipline, and machine learning helps solve many big data analytics problems. Real-time and stream data mining. Real-time and stream data mining involve analyzing data as it is generated, enabling immediate insights and responses. This is essential for applications such as fraud detection, network monitoring, and sensor data analysis. Stream data mining techniques process continuous data streams efficiently, identifying patterns and anomalies in real time. Real-time data mining requires scalable and high-performance computing infrastructure to handle the velocity and volume of data streams. This trend enables organizations to make timely decisions and respond quickly to changing conditions. Edge computing and IoT data mining. Edge computing brings data processing and analysis closer to the data source, reducing latency and bandwidth requirements. In the context of the Internet of Things, IoT, edge computing enables data mining on IoT devices, such as sensors and embedded systems. This allows for local analysis of data, reducing the need to transmit large volumes of data to the cloud. Edge computing and IoT data mining improve responsiveness, enhance security, and enable new applications in areas such as smart cities, industrial automation, and healthcare monitoring. A scaling approach for smaller off-grid systems includes a forecasting component to improve the symmetry between PV output and daily load curve. Challenges and limitations of data mining. Data quality is a critical factor affecting the accuracy and reliability of data mining results. Noisy data, incomplete data, and inconsistent data can lead to inaccurate patterns and misleading insights. Data cleaning and pre-processing techniques are essential for improving data quality and reducing the impact of noise. Organizations must invest in data quality management processes to ensure the integrity and reliability of their data. Noisy data contains data, which needs some pre-processing methods after extraction, like replacing missing values, standardization and outlier, extreme data. Scalability and performance issues. Scalability and performance are significant challenges when mining large datasets. Data mining algorithms must be able to handle increasing data volumes and complexities efficiently. Scalable data mining techniques, such as distributed and parallel data mining, are essential for processing big data. High-performance computing infrastructure, such as cloud computing and GPU acceleration, can improve the performance of data mining algorithms. Organizations must carefully consider scalability and performance requirements when selecting data mining tools and techniques. Interpretability of complex models. Complex data mining models, such as deep neural networks, can be difficult to interpret, making it challenging to understand how they make decisions. This lack of interpretability raises concerns about transparency, accountability, and trust. Explainable AI (XAI) techniques aim to improve the interpretability of complex models, providing insights into how they work and why they make certain predictions. Interpretability is particularly important in domains such as healthcare and finance, where decisions can have significant consequences. The black box nature of some algorithms can undermine trust and hinder adoption. Data mining has emerged as a crucial field for extracting knowledge and insights from vast datasets. From business intelligence to scientific discovery, data mining transforms raw data into actionable intelligence, driving innovation and decision-making across industries.